Hello, everyone. It's a great pleasure to have Basak Kucuk today in the topology seminar. She's joining from University of Göttingen, and she will tell us about conjectures of Klein and Williams for the equivariant fixed point problem. So, Basak, please take it away.
Okay, thank you very much for the invitation. Today I will talk about the conjectures of Klein and Williams for the equivariant fixed point problem. John Klein and Bruce Williams developed an obstruction theory for equivariant fixed point problem. And then they stated a conjecture about their invariant. And after that, they applied their equivariant fixed point problem to the n-periodic point problem. Then they state another conjecture, which is similar to the first one. And today I would like to talk about those conjectures, and I would like to present my findings related to these conjectures. This is my PhD project, one part of my PhD project. So let's start with equivariant fixed point problem. Equivariant fixed point problem asks the following question. Given a group G and equivariant self-map on G space X, the question is, can we find an equivariant homotopy from this map to another equivariant map such that new map has no fixed point? So here G space means we have a group action on the space X, and equivariant map, sometimes we call G map, means the map is commutes with all the elements G in G. During the talk, we mostly consider the equivariant manifolds or equivariant smooth manifolds. Okay. So if we consider the non-equivariant case, that is, if we consider the trivial groups, of course, the classical obstruction is the Lefschetz number, as we all know from first algebraic topology course. Remember that the Lefschetz number is defined by alternating summation of this traces of these induced maps, and Lefschetz number is an obstruction for this problem in the non-equivariant case because of the famous Lefschetz fixed point theorem, which says that when we have a compact triangulable space and when we have a self-map on that space, if this map has no fixed point, then its Lefschetz number is equal to 0. And it is well known that the converse is not true. And there is a more refined invariant, which is called Nielsen number. And this Nielsen numbers is more refined in the sense that this gives the converse of the Lefschetz fixed point
This
theorem.
number is homotopy invariant. This number LF. What can you back to the last page? This number is Leipzig number. It's homotopy invariant. It's homotopy, right?
Yes.
Yeah.
It is homotopy invariant.
So it can be okay.
Yes, it is defined by traces of
by
this.
homology. Okay.
Yeah. So this is homotopy invariant. So we can also change the Lefschetz fixed point theorem homotopic maps. Yes. So thank you very much. And Nielsen numbers is more refined invariant because of this theorem. For a self-map on a compact Euclidean neighborhood retract X with dimension of X is greater than or equal to 3, this self-map can be deformed, in other words, homotop, into a fixed point free map if and only if the Nielsen number of this map is equal to 0. So one remark here, the dimension condition is necessary because Jung showed that for any two-dimensional connected manifold with negative Euler characteristic, there exists an onto self-map with Nielsen numbers is equal to 0, but we cannot homotop this map to a fixed point free map. So this was the motivation and classical invariance. In the non-equivariant case, we will move on to the equivariant case and we will see answers for fixed point problem in the equivariant setting. First, we will see a definition of Nielsen numbers because during the rest of the talk, we will mention about Nielsen numbers a lot. So I will give a quick definition of Nielsen number. Nielsen numbers is defined geometrically. It's defined by using fixed point indices, and when we have a self map on a manifold or on a G manifold, the fixed point index of that map is defined locally. So it is enough to define the fixed point index of this form of maps. This map is from U to Rn, and U is open subset in Rn. And we assume that the set of fixed point of F is compact. Then the fixed point index is defined as follows. It is the image of this class, the coefficient of image of this class under this map. This is the induced map of identity minus F, and this class SNF is the image of fundamental class under this map. So right now it may seem a little bit hard to compute, but when we have for example, single fixed point, or when we have a generic fixed point, there is a easier formula to compute this index. We will see later when we are seeing concrete examples. Right now, so this is the fixed point index. It is enough to know like that. And so we will define the Nielsen numbers using the fixed point classes. That means two fixed points x and y are in the same fixed point class if and only if there is a path alpha from x to y such that alpha and f of alpha are homotopic relative to the endpoints. And we denote the set of fixed point classes as fixed CF. We will use this notation later. And so some of the fixed point classes is called essential. If we take this class X, the fixed point class of F, this means this contains the fixed point X. Then this class is called essential if this class is called essential if it is. Sorry, is there a question?
I think it's background noise there.
Okay.
Sorry.
It's called, no worries. It's called essential if it is fixed point indices is not equal to 0. And here, this IFX, the fixed point index of this fixed point class is defined by using an open ball U such that U contains this fixed point class, and intersection between U and the set of fixed point of X gives exactly this fixed point class. We can choose such a U, and this defines the fixed point index of this fixed point class. And the Nielsen numbers is just now can be computed from this is the number of essential fixed point classes of self-map F. So this is the Nielsen number. And now let's turn back to the equivariant setting. First answer for equivariant fixed point problem is given by Fadell and Wong. They use more classical techniques to prove that theorem. And they gave an answer for this problem for compact Lie groups and compact smooth G manifolds. Let's this sequence be a admissible ordering of isotropy types of M. That means we have subgroups HIs, the subgroups of G. We are taking the conjugacy classes of these subgroups, and each subgroup is an isotropic group of M. And there is an associated filtration of this sequence, which is defined here. This is a filtration for M, the manifold M. And assume that for each I, the while group is finite, and while group is defined as here. It is the normalizer of HI mod HI. And if we assume these two-dimension conditions, then a G self map on M is G homotopic to a fixed point free G map if and only if the Nielsen number of these induced maps are equal to 0 for each I. This induced map means this is a induced map of F on HI fixed points of M. So in this case, the obstruction is given by bunch of Nielsen numbers. This gives one answer for equivariant fixed point problem. There is a more modern approach by Klein and Williams.
I have a question, Basak, maybe before going into the equivariant setting. So are the Nielsen number and the Lefschetz number related to each other somehow? Or?
They are. So, for example, when we have an identity map, I think both number gives the Euler characteristic. But other than, I think there is no direct relation. I mean, we cannot compute from one of them to other one. So mostly they give the different numbers.
Okay, so is Nielsen's more refined because it looks more homotopical than the other one, which is homological?
Yes, it's more refined because it gives the converse of the Lefschetz fixed point theorem. So
I see. Okay.
Yes. In here, the converse is not true. We can say that Lefschetz number is an obstruction for this fixed point problem, but the converse is not true.
Okay. Yeah. Thank you.
Thank you for the question. So there is a more modern approach by Klein and Williams. They developed an obstruction theory for equivariant fixed point problem by using parameterized equivariant homotopy theory. And their answer, so they gave an answer for closed smooth G manifold M, where G is finite group in this case. So there is an invariant LGF which lies in equivariant frame-Bordism group of this space. This LFM is called twisted loop space, and it's defined by paths on M, such that the f of the start of the path is equal to the end of the path. And this invariant vanishes when f is equivariantly homotopic to a fixed point free map. And for the converse, assume this invariant is equal to 0 if these two-dimension conditions satisfy, which are actually similar to the conditions that are in previous theorem. Then f is equivariantly homotopic to a fixed point free map. So I will now state the conjecture of Klein and Williams. Klein and Williams wonder whether their invariant is there a relation between their invariant and the Nielsen numbers, because if you look at the previous theorem, the obstructions is given by a bunch of Nielsen numbers. But first, let me remind you the equivariant frame-Bordism group quickly. The geometric definition is as follows. It is defined as the set of equivalence classes of triples under the relation of Bordism. Each triple consists of G manifold M of dimension n when we have when we are considering the nth degree, an equivariant map from M to X, and a stable equivariant bundle isomorphism phi. I won't go into the very much details of Bordism theory, but we can also think this group algebraically, because the Pontryagin-Thom construction gives an isomorphism from equivariant frame Bordism group to equivariant stable homotopy group of X, which is defined by this colimit. This is the equivariant homotopy classes of maps from this sphere to this space sphere wedge product X plus, and X plus means is X disjoint union with base point, single point. So this is the group where our invariant lives in. And the conjecture is as follows. The Nielsen numbers of the induced maps on the fixed set for each conjugacy class of subgroups H of G can be computed from the projection of Klein and Williams invariant LGF onto the corresponding summand in the Tom-Dick splitting. So in our case, the Tom-Dick splitting is the following. Equivariant frame Bordism group of this twisted loop space can be decomposed as a regular frame Bordism group in the 0 degree of this Borel construction. So here, this is the Borel construction of Y group, and remember, Y group is defined by normalizer of this group H, mod H. So from now on, we would like to know the composition of the Klein and Williams invariant under the Tom-Dick splitting. But first, to be able to understand that, we need to give a rough construction of the Klein and Williams invariant LGF. So as I already mentioned, Klein and Williams use equivariant parameterized homotopy theory. So I will mention about two categories they use. These are categories of G spaces over a fixed space. One of them is defined as follows. Let B a G space. Define the category of G spaces over B as follows. The objects are G spaces X equipped with a structure G map from X to B. These objects is called G spaces over B, and the morphisms are just G maps which are compatible with the structure maps. So this category is denoted as TBG. Sometimes we call fiber-wise spaces or G spaces over B. And there is a retractive version of this category of parameterized G spaces over B again. This time our objects are again G spaces over B, but we have extra structure maps from B to X such that the composition of two structure maps gives the identity map on B. So these are also called section maps. And the morphisms, similarly, G maps between these objects which are compatible with both structure maps. And so these are the categories that we will use. And it is important to note that they are actually model categories. So I don't want to go into the details of model categories, but we can think a model category as we have special kind of maps which are called weak equiluses, fibrations, and cofibration. And these maps satisfy some certain axioms. And when we have a model category, we can define homotopy classes of maps at that category. So we will use those kind of tools from model category. But since I would like to construct a Klein and Williams invariant, I won't go into the detail. To construct the invariants, consider the lifting problem for the following form. So we have a map from M to M cross M, and this is the graph of F. We have a self-map F on M, and this is defined by M maps to M comma F of M. And here, M cross M minus diagonal means this delta means the diagonal of M cross M. And actually, Klein and Williams developed this obstruction theory for more general problems, which is called intersection problem. This is So they developed obstruction for special kind of lifting problem, and this is an example of those lifting problem. And actually, for some homotopical reasons, finding a finding an obstruction theory for this lifting problem is the same as finding a obstruction for equivariant fixed point problem. So we will define the invariant for this lifting problem, and it is so it's constructed as follows. First, consider this map, this obvious inclusion map from M cross M minus diagonal to M cross M. We can think this object M cross M minus diagonal as a G space over M cross M because we have a structure map, and since this TBGs and RBGs are model categories, we can actually convert any given map into a acyclic cofibration and then fibration. That means we have a space E which is weakly equivalent to M cross M minus diagonal, and there is a cofibration from this M cross M minus diagonal to E, and we have a map from E to M cross M, and that is a fibration. So we will use this space E, and actually we will consider the pullback of E along the graph of F. And after taking this pullback, we have a structure map from this pullback to M. So we can think this object in the category of G spaces over M. So we will use this object later. First, I need one more definition. So in the classical stable homotopy theory, the suspensions and reduced suspensions are very important for us because of the Freud and suspension theorem. Everything becomes everything stabilizes eventually. So that's why, so that's the main idea of stable homotopy theory. So there is an analog of this suspension and reduced suspension in the category of G spaces over a fixed space B. But right now we are thinking about the G spaces over M. So this analog is defined as follows. Let E be an object in any object in TMG. The unreduced fiber-wise suspension of E over M is an object in TMG defined as follows. So we are like in the normal suspension. First, we take the cross product between E and the closed interval, and instead of collapsing the bottom and top part into a point, we are collapsing into M. So this is a space over M, and there is an also reduced fiber-wise suspension. That means after taking this fiber-wise suspension, we are collapsing M cross interval into a M. And okay, we needed this fiber-wise suspension because we have these type of cohomology groups. This is an equivariant cohomology with coefficients R in a certain parameterized equivariant spectrum. I didn't define a parameterized equivariant spectrum, but in our talk, we will only consider this special spectrum. This is an example of a parameterized equivariant spectrum, and we can think of this object as a sequence of spaces, and in the nth level we have nth reduced suspension over M of this object, fiber-wise suspension of this pullback E. Remember, this E is a certain space that we obtained from here. So this is a weak equivalent to this space. Okay, so this is a certain parameterized equine spectrum, and this group we will only consider the 0th degree, and it is defined as follows. It's the colimit of homotopy classes of these maps in the category of parameterized space G spaces over M. And these maps are from nth times reduced suspension over M of M plus to nth reduced suspension over M of this fiber-wise suspension. Here M plus means is M disjoint union with M. It is not M disjoint union with point because we are in the category of G spaces over M, so we have double M here. Now, finally, we can define a class which will define the Klein and Williams invariant. So this class lives in this group and obtained by the following map. This is just the obvious inclusion map. So we have M disjoint union M here, and we have suspension over M. So we remember we have M at the bottom and we have M at the top, and this map is just sends the M to the fiber-wise suspension of this object. This invariant, this class S defines the Klein and Williams invariant because we have an isomorphism from this cohomology group to equivariant frame Borgism group of twisted loop space. So this was the one of the hardest thing to analyze for my PhD thesis, I would say. After observing this, it is so we obtained the following decomposition. So our aim was to decompose LGF, the Klein and Williams invariant, under the Dieck splitting, but the LGF actually defined on this cohomology group, and it is easier to decompose this element in here because this S map is actually simple map. It's just the inclusion, and here, by the way, this is a special case of Klein and Williams theory. I already mentioned that they gave an obstruction theory for more general problem, and in the more general setting, this is not necessarily isomorphism, but only in this special case when we have a self map F on M, and this group we have isomorphism, and by using this isomorphism we can conclude that LGF from this splitting we can directly conclude that LGF is decomposed as follows. And another thing to observe is that the Dieck splitting thing here becomes of this form. So we had a Borel construction at that point, but we are in the 0 degree, so we are lucky because we could able to rewrite this this Borel frame Borgism group of Borel construction as of this form. So here the Klein and Williams invariant decompose as like this, and this L F to the H means this is an obstruction for a fixed point problem in a non-equivariant case. That means we are taking the group trivial group. So this gives an obstruction for F to the H, and F to the H is induced map of F on the H fixed points on M. So H's are subgroups of G. I think I forgot to tell you, sorry, this H is indexed, so this summation is indexed over the conjugacy classes of subgroups of G. And but we need to also take into the account the Y group action. So this bar denotes that it is the induced element of LG F to the H under the quotient by Y group WH. I try to explain as much as I can, but I won't give the proof. But rather, I would like to mention that this class in the so we decompose equivariant invariant in the terms of non-equivariant invariants, and there is a relation between this invariance with Nielsen numbers in the non-equivariant case. Actually, each L, F to the H's are identified with Reidemeister traces, and the Reidemeister trace is defined as follows. This is another invariant. This is also known as generalized Lefschetz trace or generalized Lefschetz number. And this is also another obstruction for fixed point problem in the non-equivariant case. It is defined as follows. Again, we have a self-map on a compact manifold M. The Reidemeister trace is the image of this class under the injection map here. And this class is summation of all the fixed point classes of F together with fixed point indices of this fixed point class. And this element lies in free abelian group of this fixed point class F. And we have injection map here. This is a free abelian group of this set. We have a twisted conjugate relation on the fundamental group M. So we will so this is the where Reidemeister trace lives in. And it is already known in the literature that this Klein and Williams invariant in the non-equivariant case is identified with Reidemeister trace. This is left as a remark in the Klein and Williams first paper without proof, but it is not hard to prove when we are considering closed compact smooth manifolds, because we can use the transversality and intersection numbers when we are in the smooth category. And actually, Kate Ponto developed this identification in more general spaces, and this identification is done by introducing a generalization of the trace in symmetric monoidal categories to a trace in bicategories. But I don't want to go into the details at this point. It is just enough to know that this class is the same as Reidemeister trace. And by the way, so you can, maybe you have already observed that, but I should say that from Reidemeister trace we can compute the Nielsen numbers immediately, because Nielsen numbers is just the number of non-zero coefficients of this class. And by using this corollary, combining this corollary with our splitting result, we can directly conclude that this gives the composition of Klein and Williams that we aimed in the each. So okay, we have conjugate classes of subgroups here, and this I is indexed over connected components of M to H fixed points of M. Here we needed to consider the component connected components separately, because this isomorphism is true when we have connected manifolds. And the summation of Reidemeister traces of F to the H I, here F to the H I is induced map on M to the H in ith component. This summation gives the Reidemeister trace f to the h. And so we are almost done, it may seem. So we identified the Klein and Williams with Nielsen numbers that has been conjectured, but we need to take into the account the Y group action actually. So here this bar denotes, similar to the previous one, denotes the quotient under the Y group of the Reidemeister trace. So the question is now whether we are losing some information or not after taking this quotient. So it is clear that when the Reidemeister trace is equal to 0, the induced then the induced Reidemeister trace is equal to 0. But what about the converse? Are we losing some information or not? It turns out that we don't lose any information because of the following observation. Given a G self map on X, on a G space X, the fixed point index of fixed point class X is the same as fixed point index of the fixed point class Gx for all G in G. So direct conclusion of this observation is that the Reidemeister trace is equal to 0 if and only if the induced Reidemeister trace is equal to 0. So from this observation, we can say that we can compute, or at least the Reidemeister trace and a bunch of Nielsen numbers of f to the h contain the same amount of information for equivariant fixed point problem. So this resolves the one conjecture. For the rest of the talk, I would like to talk about one application of this equivariant fixed point problem to the periodic point problem. So given a self-map on a closed smooth manifold M, this time this is not equivariant manifold, consider the Fuller map associated to this map, which is an Zn equivariant self-map on M to the N, defined by as follows. So nth tuple maps to this nth tuple. And if we substitute this Fuller map into the main theorem of Klein and Williams invariant, main theorem of Klein and Williams, we obtain the following theorem. So Klein and Williams obtained the following theorem. There is an homotopy theoretically defined invariant. This time we denote L and F shortly, but we just substitute Fuller map as a self map and Zn as a group. This lies in Zn equivariant frame Borvism group of this space. This is just the unraveling of the twisted loop space of Fuller map, and in this time, it is consisting of n tuples of paths on M, satisfying this identity for all I. This is an obstruction to deforming F to n periodic point-free self-map. And a point X is called n-periodic if nth iteration of f of x is equal to x. So this is one application, and another result using completely different techniques by Jerieski. He gave an answer also for periodic point problem. He proved that any self-map on a closed smooth manifold of dimension is greater than or equal to 3 is homotopic to a map without periodic points of period n if and only if Nielsen numbers of kth iteration of f is equal to 0 for any divisor k of n. Okay. Another conjecture is also related to this, whether the Klein and Williams invariant is there a relation between Klein and Williams invariant L and F or with these Nielsen numbers. And Klein and Williams also proved that in this case, this group can be decomposed as follows. This equivariant frame-Bordism group decomposes as a free abelian group of this set. This is the set of equivalence classes of fundamental group with following relations. So the first relation is actually a twisted conjugacy relation, and the second one is this relation. And here, rho is a map on the fundamental group defined by loop maps to this loop, where omega is omega is a chosen path from base point to f of base point. And if we only consider the first relation and not the second one, then this group, free abelian group on this set, would be the group that the Reidemeister trace of f to the k lives in. And remember, we can compute the Nielsen numbers of f to the k from Reidemeister trace of f to the k. After proving this theorem, Klein and Williams wondered that the following conjecture they wondered that the following is true or not. Let nkf be the number of non-zero terms in lnf. Remember, lnf lives in here and it is decomposed at here. And nkf is the non-zero coefficients of L to K and F. This is expressed as a linear combination of the basis element in this group. Then they stated that this NKF is the same as Nielsen numbers of F to the K. So, we concluded that one is equal to 0 if and only if the other is equal to 0, but they are not exactly the same. So in the end, we will give example. But first, so this is the last proposition that I would like to talk about today. Then we will move on to the example. We obtain that this number is vanishes if and only if the alt fold of f, Nielsen numbers of alt fold f vanishes. I will try to give a sketch of the proof, but I would like to also spend some time for example. I will try to make a little bit quick. L is equal to n over k. It is not hard to see that there is a one-to-one correspondence between the set of fixed point classes of this Fuller map, this induced Fuller map. So remember, Fuller map, Zn equivariant, and when k is a divisor of n, this is the subgroup. So we need to think about all the subgroup. Actually, we are thinking about the conjugacy classes of subgroups. Zn is a abelian group. So every subgroup is a conjugacy class of subgroups by itself. So okay, we need to think about also subgroups. This induced map, it is not hard to see that the fixed points of this induced map is of this form. This tuple where X is L periodic. So the fixed point classes maps to this fixed point classes of F to the L, and this is one-to-one. So it's straightforward to show that. And after showing that, we claim that the fixed point index of this class, of this induced Fuller map, is the same as fixed point index of F to the L of this class. So once we show that, we can conclude that the Nielsen numbers of this Fuller map, induced of Fuller map, is the same as Nielsen numbers of F to the L. And remember this NLF computed from the can be computed from the Nielsen numbers of this Fuller map, this induced Fuller map, but they are not exactly the same because we are taking the Y group action. So this is the induced version of Nielsen numbers of this Fuller map, but we already showed that once the Reidemeister vanishes, if and only if the induced Reidemeister trace vanishes. So it is enough to show that this identity. And actually, it suffices to show this equality because m to the n to the zk fixed point of m to the n. And I think I didn't mention the Zn action of m to the, Zn action of m to the n, but this is the obvious action. Just rotates the component wise. We have nth components, and by using that action, the fixed sets, zk fixed sets of m to the n is m to the l. And this induced Fuller map actually corresponds to this Fuller map on m to the l. So it is enough to show that the fixed point index of this Fuller map at this point is equal to the fixed point index of f to the l at x. We will use the following identity to show that show these indices are the same. We will consider the generic fixed point. That means this that determinant is not equal to 0. So in that case, the fixed point index is either 1 or -1. And the indices are the same because they have the same determinant. This can be shown by using actually linear algebra, by using the properties of determinant of the block matrices, because this Jacobian of this Fuller map becomes like this. And each entry we have m cross m block matrices, where m is dimension of the manifold. And this is the idea of the proof. Now in the remaining time, I will give the counter example that shows that this L and F are not the same as Nielsen numbers of F to the L. So we will consider this manifold Y. This is a sphere with 4 open ball removed. This is a manifold with boundary. We mostly consider the closed manifolds today, but we can make this manifold compact by taking 2y and gluing 2y's along their boundary. But simply we will consider the manifold Y because this won't change the calculations and it will just because remember the fixed point index is defined locally, so it won't change the calculations. Now consider Z4 cross Z2 action on S2. We will define an action on manifold Y, and then we will define the map from that action. Then we will consider the two periodic points of that periodics of that map. Then we will calculate the Klein and Williams invariant and compare with the Nielsen numbers. Okay, the generator of Z4 rotates each point by pi over 2 radians about the y-axis. I can also show, G rotates pi over 2 radian along this y-axis, and H reflects each point across the zy plane. H is a generator of Z2 along this plane. Okay. H. Okay. Now consider the map which is defined by composition of H and G. So we have two periodic points. Let me show the two periodic points. If we take this point, then this X maps to here by H, and G fixes that point here. So this is the f of X. And if we apply f of X one more time f, then we became the same point that we started. So we have two periodic points. X is two periodic points, and similarly, f of X is also two periodic points. And these are the only two periodic points of f. And we have holes in here. We have holes because we wanted to make X and f of X are not the same fixed point class. So they are not in the same fixed point class because y is f of X in this case. Because there is no path alpha from X to Y, f of X, such that f square alpha and alpha are homotopic relative to fixed point. So they are not in the same fixed point class. Okay, now let's continue to the calculations. So we will calculate the fixed point indices of f square at the point X and fixed point indices of f square at the point f of X. But actually, one can show that these indices are the same. I will skip the reason now, but so they are just the same. And we can compute this fixed point index at X because, so consider this loop. Consider this S1 that contains X. So f square induces antipodal map on that red circle. And actually, the fixed point index of X is just the degree of identity minus f square on that red circle. And so this degree gives 1 because identity minus antipodal, we can compute its degree. And so our indices are 1. That's why the Reidemeister trace of f square is equal to this. And therefore, because their indices are the same, we prove that one. And the Reidemeister trace of a Fuller map on y cross y is equal to this one. So remember, now we need to take this element under the while group action. And here this while group means here we have W1 because we consider the trivial subgroup. So this Fuller map is Z2 invariant, and we have two subgroups, trivial one and the Z2 itself. And this while group is this case is isomorphic to Z2, and Z2 action on on this element is just rotating the tuples, rotating the components. So this class and this class are the same under the quotient of Z2. So reduced Reidemeister trace is equal to this one. And we have the second one. We need to compute the second one. We have two subgroups, the subgroup Z2 itself, but in this case, we don't have any fixed points, so there's nothing to calculate. It's just 0. Therefore, the Klein and Williams invariant is equal to this. From here, we don't get anything, and from here we have this this class. Therefore, and the first one is related with Reidemeister trace of F. And therefore Nielsen number of F and N1F, the first coefficient of the first this class, is equal to 0. In this case, they are the same, but in the second, if you look at the second part, the Nielsen numbers of F squared is equal to 2 because we have two non-zero coefficients, while the N2F is equal to 1 because there are only one non-zero terms. So this is all I would like to talk about today. These are my references here. Thank you very much for listening. Do you have any questions?
Okay, thank you, Basak. Just a second. Okay, yeah, sorry, there was a small interruption here. Okay, thank you, Basak. So any questions for Basak?
Thank you, Basak. Thank you very
Thank
much.
you. Thank you very much for listening.
So this F in your example is a homotopic sum self-map that has no fixed points? Because you said
So F has no fixed point, I guess. Or yes, because the Nielsen numbers is equal to
okay.
0.
Yes.
Yeah.